Okay, thank you, Leo. First of all, I'd like to thank the organizers for giving me an opportunity to visit this very nice place and to give a series of lectures on exclusion processes and something related. Second, I'd like to thank you all for attending this lecture. Okay, so my focus is basically on exclusion processes in 1D, ASAP, TASAP, and so on. But the aspects I'm going to explain is somewhat related to physics side. So I think at the beginning of the first lecture, I want to spend, I don't know, like 10, 15 minutes to explain some motivations from physics side. So this is why I'm using slides at the beginning. But after 15 minutes or so, I switched to Blackboard. Right? Okay, so let's begin. Pretty simple first page. Okay, so so we are interested in kind of large-scale behaviors of basically stochastic processes like exclusion processes, but some motivations, at least for me, is coming from statistical mechanics. So this is kind of one field in physics. And this is a kind of big theory which tries to explain various properties of matters, which are around you, from microscopic dynamics. By microscopic dynamics, one can mean, this is not working. Is there another thing?
It might be working, but it's not visible.
Yeah, 2 weeks. No, yeah, it's now working. So, okay, so maybe one question. Do you have some physics background? Do you know Schrödinger equation, for example? Are there some people who don't know Schrödinger equation? Okay, that's. What about Newton equations? Are there somebody who don't know Newton equations? Okay, who don't know Newton equations? Okay, so this is, in this lecture, I don't, we don't work on quantum systems, so Newton equations are enough. So please relax. So anyways, there are several ways to describe microscopic degrees of freedom in physics, and one is the so-called classical one, using the famous Newton's equations of motion. So, you know, mass times acceleration is equal to force, right? But of course, matters consisting of atoms and electrons and so on, very microscopic, very, very tiny objects, which are not really described by Newton's equation. So we have to use Schrödinger equation. But from the point of view of statistical mechanics, in which we want to explain large-scale behaviors from microscopic degrees of freedom, in many cases we can use either of them. So at least in these lectures, we are thinking of some classical systems, which many particles are interacting, and we're interested in more macroscopic behavior of these interacting systems, right? And in statistical mechanics, there are kind of two aspects. One is about equilibrium systems. Also in probability theory, especially for stochastic systems, we sometimes talk about equilibrium measures, which means usually stationary measure, invariant measure. But in this case, it may not be really related to this equilibrium system, which I mean in statistical mechanics. In statistical mechanics, if we talk about, when we talk about equilibrium systems, it means that thermal equilibrium. So we are supposing that a situation in which a matter is surrounded by environment with uniform temperature, and after a long time, the matter has the same temperature as the environment. So this stationary situation is called thermal equilibrium. And for this particular situation, some fundamental principles are known in statistical mechanics and the thermodynamics. In thermodynamics, maybe you have heard of the maximization of entropy. One can define the notion of entropy, and the maximization of entropy gives you the state which is in thermal equilibrium. And from more microscopic point of view, which is more related to statistical mechanics, we also know kind of measure for microscopic state, and this is given by the so-called Gibbs ensemble, so which is written in this way. So beta is so-called inverse temperature, defined by 1 over kBT. So T is the temperature, which is non-negative real number, and kB is the so-called Boltzmann constant. So there's some value, but it's not really important here. Anyway, so this is a positive parameter, which is related to temperature. H is the so-called Hamiltonian, which specifies the state, microscopic state of the system we are interested in. And for classical case described by Newton's equation, so this H is basically the energy of the system, which can be specified by giving positions and velocities or momentums of all particles in the system. In quantum system, this is just an operator, which is which describes the system. But yeah, anyway, so this Gibbs ensemble says that a state which has energy appears proportionally to the probability which is given by e to the power minus beta h. So this is the prescription for the probability of finding system with energy h, or Hamiltonian h. And z is just a normalization constant called the partition function in statistical mechanics, right? And by using only this prescription, we can describe many interesting physical phenomena, and notably the phase transitions. You know, so there's a phase transition between water and ice and vapor, and there are many other phase transitions. And at the critical point where the phase transition occurs, there are so-called critical phenomena appearing, which shows universal behaviors of various systems and models. How to say? So of course, many properties of matters are very different depending on, it depends on what matter and other matters. But at the phase transition point, there's a strong universality, which means that several important properties about the phase transitions are shared by many models, materials, and so on. And we are mostly interested in this universal aspect in equilibrium statistical physics. Okay, so this is the kind of basic knowledge about equilibrium statistical mechanics. But we are more interested in non-equilibrium situation. So there's also in statistical mechanics, we want to try to explain various properties of systems which are not in thermal equilibrium. But in this case, we don't know really some fundamental principles. So we are still trying to understand the properties of such non-equilibrium systems one by one. One common feature of non-equilibrium system is that most of them have some kind of currents of matters are flowing, energies are flowing, and so on. We are interested in average behavior, fluctuations, and so on. And non-equilibrium systems shows very interesting phenomena which are different from equilibrium systems. So classical and very nice example is given here. Let me. So this is some video from YouTube or something. So if you Google non-equilibrium and some patterns and so on, then there are many examples, right? So this is just one of them. So there are some. So this is the chemical reactions, and if you put some stimulus at the beginning, then from there you see some waves appearing from various points, and there are some interactions, and they show some patterns, right? And of course, one can see spatial patterns, but they also show some oscillative behavior, so there's also some patterns in time direction as well. So this is sometimes called spatial temporal patterns. So we are interested in such patterns, for example, how this appears, how much we can understand from microscopic principles. But this is, of course, very difficult, but there are something one can do. Okay. And as I said, big difference from the equilibrium case is that from the physics point of view, we still don't know fundamental principles. Right. Okay. So very much related to this spatial temporal pattern, we can also focus on stationary situation in which we still see some nice patterns, structures. So here's another example. Okay, so this is a very famous, again, very famous and classical one. So suppose we have some liquid, which is surrounded by two different temperatures. On top of it, we have some temperature T, and below we have temperature T plus delta T. And when delta T is just 0, of course, after a long time, this liquid becomes in equilibrium state. So temperature becomes uniform all over this material, and this is thermal equilibrium. But maybe we can put this temperature below the material to be higher than the one at top, and we can try to increase this delta T. At the beginning, nothing does not seem to be happening, but when delta T becomes large enough after delta TC, then we see that this liquid starts to rotate, and there's some structure appearing. So let's see. So if you start from some uniform initial conditions, after a while you see this nice spatial pattern. So this kind of spatial pattern also appears in stationary state. But this is different from the thermal equilibrium state. So this is sometimes called non-equilibrium stationary state, sometimes abbreviated as NES. Right? So we are interested in non-equilibrium stationary measure and what kind of structures, what kind of fluctuations are there. So this is an example of crystal shape. Of course, these equilibrium systems also can show very interesting patterns like this. But for this, we know the principles, right? In principle, by giving the Hamiltonian microscopic description and use the maximization of entropy and Gibbs ensemble, Gibbs measure, then one can describe what kind of shape appears for a given temperature and pressure and so on. But for non-equilibrium systems, we still don't know. Right. So the question, how can we study this kind of phenomena? In principle, maybe one should try to use the Hamiltonian, which describes the whole dynamics of the system. And so basically, Hamiltonian is expected to be given in this form. So this is the, now I'm assuming that all particles have the same mass 1, but this is kinetic energy and this is potential energy, which depends just on the difference of the positions of two particles, I and j. Okay, so is this okay? So this is kinetic energy of each particle, and this is interaction term. I hope it's okay for you. P is the momentum of each part. Pi is the momentum vector, px, py, pz in three-dimensional space. And if we take this, pi squared over 2, this gives you the kinetic energy of each particle. Right? And if V is 0, this is just a non-interacting particle systems. But in many cases, in which we see interesting phenomena, there should be some potential among particles. Microscopically, it is rather easy to give some description, but the question is how can we extract interesting phenomena, properties of the system large-scale behaviors of the system from this microscopic Hamiltonian description. And as you know, so if we can really solve this equation somehow for maybe general potential and for general n, that's it. One can just do it. But as you know, it is practically impossible to do such kind of studies. And it is well known that, so when n is equal to 2, when there are only 2 particles, basically it is known to be able to be solved by using some integral. But if there are more than 2, more than or equal to 3 particles, then in general, it is impossible to solve these dynamics. But of course, there are some special cases which are also related to integrable systems, for which one can do many, many analyses. But yeah, in general, it's almost impossible. But still, maybe we can try to see what's happening for simple case. So maybe, for example, of course, we are living in 3-dimensional space, but probably it's easier to study 1-dimensional case. So then now we think about Hamiltonian, in which, yeah, so momentum has only one component, p, not px, py, pz, just p, or px. And then there's some potential in 1 dimension. And we suppose that the n particles are in 1 dimension, and they are connected by some springs. And the potential is given by this expression now. Of course, when alpha and betas are 0, potential is x squared. And so this is potential. So if you take a derivative once, you get a force. So then this becomes linear in x. So this is a so-called Fuchs spring, harmonic oscillator. So one can, so when alpha and betas are 0, so the system can be solved by using Fourier analysis, as you may know. But the question was, what happens if we introduce this nonlinearity when alpha and betas are non-zero? So so this model was first introduced by Fermi Pastor-Ulam long time ago, like 1955 or so. And first they were expecting that maybe with this nonlinearity, they can observe thermalization effects. As I said at the beginning, if some matter is kept surrounded by the environment, which has uniform temperature, after a long time, it goes to some equilibrium state with the same temperature, right? Of course, and as you may know, for when alpha and betas are 0, they are just oscillating forever, so there's no thermalization. And they thought that maybe with nonlinearity, alpha and beta, non-zero case, maybe one can observe thermalization. Of course, this cannot be solved analytically by hand, so they try to use computers. Yeah, and at the beginning, they seemed to observe tendency to thermalization, but when they waited for a longer time, they observed almost a recurrent behavior. So when they started from some specific initial conditions, after some time, almost the same initial conditions was realized. So this seems to be showing some recurrence is there for this system. And this is just a numerical simulation, and they couldn't really understand. They couldn't give nice explanation. And in fact, it's still not so clear how we should really understand the long-time behavior of this system, even though this is one-dimensional, and potential is very simple. So anyway, so non-equilibrium problems are difficult in general. That's the main message here. But still, from physics point of view, this one-dimensional system is already very, very interesting, because this shows, it is known that this shows so-called anomalous transport behavior and so on. But it's difficult, right? But maybe we don't really have to solve the whole dynamics of for microscopic Hamiltonians. In many cases, we are just interested in macroscopic behaviors of system. Maybe there's a kind of shortcut. So this is related to hydrodynamics. So of course, we can think of a matter which is with uniform as just one body, but maybe we can think of a situation in which some state of the matter depends on space and time, but there's some kind of local equilibrium, and they are evolving in time. So then we could think of describing the system time-dependent and with some spatial dependence by using the continuity equations for conserved quantities which are depending on space and time. Right? So for the usual Hamiltonian, it is well known that there are three conserved quantities: density, momentum, and energy. And so we can try to write down continuity equations for these conserved quantities. If there are additional symmetries, maybe there are other conserved quantities, but we can also try to write down the continuity equation for these extra conserved quantities. Anyway, we can suppose that these local conserved quantities satisfy some continuity equation, and maybe by solving such continuity equations, we can get useful information for the systems at hand. And of course, for the usual Newton's dynamics, so this kind of continuity hydrodynamic equation is well known. And the most famous one is the Navier-Stokes equation. So this is the continuity equation for momentum or velocity. Right? And it is well known that by using this effective description of the system, hydrodynamic description of the system, one can predict many, many properties of systems which are already in non-equilibrium state, for example. For example, so this kind of patterns can be described to some extent by using this kind of hydrodynamic approaches. Right. But there are, by writing down continuity equations, now we are losing the information about fluctuations and correlations, because this is just a deterministic equation. If we specify some initial conditions, all states at a given time and space are simply determined by this deterministic equation. But in many cases, we are also interested in fluctuation effects. So in some sense, hydrodynamic equations are not enough. And from more mathematics, so in physics, we can just write down this kind of equation and try to use it. And if they match with experiments, we are happy. But from mathematics point of view, of course, we want to understand how these kind of hydrodynamic equations appear from microscopic dynamics. So the question is if we can really derive this hydrodynamic equation, Navier-Stokes equation from Newton's dynamics. And as you may know, so this is still known to be a very, very difficult problem. Okay, and as I said, if we employ this simply the hydrodynamic description of the system, we are losing lot of information like fluctuations and correlations. But so they also sometimes contain very valuable information about the system we are interested in. So we want to kind of introduce also fluctuation and correlation effects in our description. So one example of the importance of fluctuation is given by the theory of Brownian motion. So there are kind of two Brownian motions. One is a physical one, so some movement of some small particle from pollen. And there's, of course, maybe you know better about mathematical Brownian motions, which are defined rigorously. Right? But they are basically the same thing, but interests are somewhat different. And what Einstein said was that if we can measure the size of the fluctuations of the Brownian particle, then one can determine the Avogadro numbers. For this, he got the Nobel Prize, right? So in this sense, fluctuation properties of the systems contain very, very important information about microscopic dynamics. So, of course, we want to also study them. But I'll say, once we go to these hydrodynamic behaviors, such information are lost. And this should be related to some so-called chaotic behavior of microscopic dynamics. And in many cases, it is quite difficult to really study the chaos, especially for many degrees of freedom case. But in many cases, one can naively replace it by some kinds of noise effects to study fluctuation effects. So this is what we want, what we sometimes do to study fluctuation and correlation effects for non-equilibrium systems. And yes. Okay, so this is a kind of general picture behind about studies of exclusion processes and so on, at least from physics side. Okay, so now I want to switch to very, very more concrete things like exclusion processes. But are there some questions about this motivation part? Yes?
I was kind of curious if you really said, right, you can really measure the Avogadro number by, so like you take some box of particles that are acting like Brownian motions.
Yeah. Yes. Yeah. Then you should read really the original paper by Einstein, which can be downloaded easily from internet. And it's not long, like 20 minutes, 20 pages. And at the end of the last page of his paper, he mentions that 6 times 10 to the power 23. So this is really the Avogadro number.
But so, okay, but part of that comes from some actual experiments?
Oh, yes.
But how can that be? That surprises me, that it can be fine enough to rule out any other effects.
Well,
Pick up this number up to the correct precision. I mean, right? How do you guarantee that these things are really acting like true Brownian, independent Brownian motions?
Well, yeah, maybe we should discuss later. But his basic idea is to kind of use two theories from microscopic description and more macroscopic description to the same situation and try to give some matching, right? So then, by looking at the fluctuations, this is more kind of from microscopic side. But yeah, there's also microscopic description, and then if we assume that they match, then this gives us information about microscopic systems from just observing, the motion of Brownian particle, which at the time became possible to observe by microscope, right? Yeah. Okay, thank you. Other questions for this motivation part? Okay, so let's go on to more. Yeah. So yeah, this is very, very quite general, but basically it's impossible, right? So now we come to the problems for which we can do much more things. Okay, so today, maybe first I have to tell you one thing. To my surprise and to my shame, now I have some pain in my shoulder, as you may know. In the Middle Ages, like 40s, 50s, sometimes we have some pain, so I cannot go higher. So let me start from somewhere here. So I'm still in the introduction part. So after talking about very, very general and large-scale things, we come to very, very simple things, 1D stochastic systems. so let's start from the most important examples, ASEP. So this is, are there somebody who don't know ASEP? Okay, yeah, so this is a school. So this is kind of one of the most important models in the whole theory of one-dimensional stochastic processes. And so the process is called asymmetric simple exclusion process. And we consider it only on one-dimensional lattice, Z. We could think about a periodic lattice or open boundary case, but in these lectures, we mainly focus on the case on Z. And so we consider one-dimensional lattice, and on each side, there could be one particle, or the site is empty, so there are only two states per site. And each particle tries to do asymmetric random walk with rate p to the right, and with rate q to the left. The rate means that, so we are considering stochastic systems with continuous time. So in many cases, in fact, it is more useful, and in fact, easier to study discrete time dynamics. But kind of standard theory for stochastic systems have been constructed for continuous time setting. And at least in this lecture, I would like to concentrate on continuous time dynamics. And the rate means that during infinitesimal time duration dt, a particle hops to the right neighboring site with probability dt, and to the left with probability q dt. But in this situation, in many cases, we just say that with rate p to the right and with rate q to the left, right? And of course, this particle tries to hop to the right with rate p. This particle tries to hop to the left with rate q. And maybe this particle may also want to hop to the right, but because there is a particle already here, this hopping cannot occur. And in the same way, this hopping cannot occur. So this is the origin of the word exclusion, right? So there are exclusion effects among the particles. Simple usually means that particles can hop only to the neighboring sites. Of course, one can think of dynamics in which particles hop far away, but with this simple, particles hop only to the right, to neighboring sites, either on the right or to the left. And of course, the P and the Q are non-negative real numbers. Yeah. Okay, so this is the kind of definition of ASEP. Is some question? No. Okay. Some special cases are also important. One special case is when P is equal to Q. So in this case, random walk is symmetric. So this is just a special case, but behaviors of systems become very, very different, whether this is they are different or they are the same. And sometimes we are very much interested in symmetric case. And well, of course, we could also put symmetric simple exclusion process, but maybe in this lecture, I simply call this SEP. One reason is that this is more difficult to pronounce. SEP, right? So SEP is easier. So I call this SEP. there's another special case which is also very important. This is the case in which particles hop only in one direction. Sometimes we put p equals 0, sometimes we put q equals 0, but maybe in this lecture we put p equals 1, p equals 1 and q equals 0. Okay, so yeah. Of course, we could still keep p to be general, but in fact, we are now considering continuous time. And because probabilities are given by p dt and q dt, by rescaling time, we can observe one parameter degrees of freedom into time. So we can always set one parameter to be arbitrary value. Yeah, for the case of SIP, sometimes we put them to be 1/2, sometimes we put them to be 1, depending on some purpose. But anyway, we can put one parameter to be a fixed number. And in most cases, when we consider TASEP, which means this is totally, as asymmetric simple exclusion process case, then we put one parameter to be 1, right? Hopping rate to the 1. But no, in fact, sometimes, yeah, we keep these parameters. Okay. There's also one more important variant of TASEP, which is the Qtative. So this is a generalization of TASEP, which is different from ASEP. In the case of TASEP, particles hop only in the right direction, and the particles hop only to the right neighboring side with always rate 1. But in this generalized model called Qtative, particles can hop. So this is also TASEP. So of course, at each lattice site, there's at most one particle. So there's exclusion. But and each particle can hop still only to the right neighboring side. But the hopping rate can depend on the distance to the particle ahead. So sometimes we write like a gap. So this is the gap. So this, suppose this is the jth particle with position xj. Then this is xj minus 1. And the gap is xj minus 1 xj minus 1, right? When gap is 0, for example, when xj is x and xj minus 1 is x plus 1, then this becomes 0. So this is 0, and this is 0. So this particle cannot hop to the right. So this reflects the exclusion rule, right? And in this case, yeah. So this Q and this Q in ASEP are different, right? But this is a different parameter between 0 and 1. Again, by rescaling time, maybe one can introduce 1 minus q. And then we could also consider the limit in which q goes to 1. But yeah, this is a minor comment. So these are all exclusion processes we want to study in this series of lectures. And of course, there are many variants. Yeah, you could think of various generalizations you want to study. But in many cases, of course, it's difficult to study detailed properties. But for these systems, ASEP and Qtative and some related processes, we can actually study many, many properties of them. But still, for more general setting, so now let's recall the kind of motivation which I explained by using slides. So we are interested. So we are thinking that the systems is described by microscopic dynamics given by Newton's equation, and we're interested in macroscopic behaviors, hydrodynamics, fluctuations, and so on. For these systems, we can ask the same questions, right? And we are also interested in stationary, non-equilibrium steady state, right? And of course, because of this rule, obviously, at least except for this step case, there should be some non-zero current. Which is characteristics for the non-equilibrium systems, right? And we can ask what is the stationary measure for this case. So this is already a question, especially for the beginners. So what would be the stationary measure for this system? Right? So in the case of equilibrium systems, as I said, there's a standard prescription that the stationary measure is given by Gibbs ensemble, Gibbs measure. But this is already a non-equilibrium system, so we have to first specify the stationary measure. What is that? And from our physics side, we are also interested in the case with boundaries in which particles can enter and go out of the systems. And there should be some stationary measure. What is that? Right? But anyway, at least we can ask such questions before really solving them. And we could be also interested in hydrodynamic behaviors. So this is still microscopic description of some systems. But what is the hydrodynamic description of the system? And we are also interested in fluctuations and correlations. Right? Hydrodynamic theory for this kind of stochastic processes have been developed some decades back, like in the 80s and 90s. So there is a kind of general theory already to derive hydrodynamic description of the systems for rather generic dynamics for this hydrodynamic equation. But more recent studies have been focusing on this part, fluctuations and correlations. And it is possible to study these kind of aspects only for very, very special cases. By special cases, I mean basically the ones related to integrable systems. So this is why this summer school is called integrable probability, right? So there are some models which are related to integrable systems. And for these cases, we can also study these aspects, right? And we are very much still interested in these aspects of various stochastic processes. Of course, in principle, we should try to kind of generalize our methods and arguments to apply to get the results for more general cases. But for the moment, it's still very difficult. So we are restricted to study very, very special cases related to integral systems. But so this is a kind of a heuristic description, definition of the processes. But maybe we want to formalize it more carefully a bit. So of course, this is the stochastic process, especially Markov process. So first we should specify state space. But of course, naively, it's pretty obvious. So this is related to what kind of configurations are possible for ASIP. Of course, a configuration of ASIP can be specified by giving occupation number at each site, which is denoted by eta I, which takes a value 1 when I is occupied. And becomes 0 when the site I is empty. And so this is the whole state space. And the dynamics of these processes are usually defined through the generator. For a function which is so-called cylindrical function on this state space, in fact, we don't actually really use this generator so often in the subsequent lectures. So, but maybe I still want to mention that there is such description. Basically, this describes the time evolution of the function, right? And sorry. Eta j plus 1 means that this is configuration eta. But eta j and eta j plus 1 in eta exchange it, swapped. And you see, of course, this corresponds to the hopping to the right. This corresponds to the hopping to the left. And depending on these changes, we should consider configuration in which j occupation numbers at sites j and j plus 1 are exchanged. Right.
Is that true that only one of these are there?
Hmm? Yeah. In fact, yeah. Well, because of this, maybe. Yes. Yeah. Okay. Mm-hmm. And yeah. I don't really explain the kind of general construction of the time evolution for ASIP on Z, but for this kind of stuff, you should refer to the famous book by Liggett, for example. Okay. But more practically, we should think that this generator gives us a way to calculate the time evolution of the expectation value. So this is a function depending on some configuration eta, and we are interested in expectation value because we are considering stochastic processes. So there is associated expectation. And we are interested in time evolution of some expectation value of physical quantities. And this is given by this generator. For example, maybe we're interested in the time evolution of the density. Right? In which we should consider a function which is given by eta k. So we are interested in the density, average density at site k. In this case, we should take f to be eta k. So expectation is, in many cases, we also denote by bracket. Then by using this kind of definition of the generator and this function f, you can try to write down the evolution equation for this average density at site k. Which way I should write? In this case, we could also try to, maybe I want to change k to j. Of course, we can try to write down this equation by using the definition. But in this case, at least, we can write down the equation by just using the rules of the process. Yeah, when this eta j changes, this could change when j minus 1 site j minus 1 is occupied by a particle and site j is empty. In this case, with weight p, particles hop to the site j. So this should contribute, right? In the same way, from the site j plus 1 with rate q, this should contribute. These are the kind of only positive contributions. But we should also consider the case when particles go from the site j to j minus 1 or j plus 1, so that's kind of escape rate. Then, when there is a particle at j, and when there is no particle at j minus 1, this contributes with rate p. Sorry, the other way, right? P. No. So this is the opposite. And so this, plus. And q. This is the rate. Right? But this can be also checked by using definition. Okay. Now you can see that this can be rewritten in a little bit suggestive form. In fact, the right-hand side can be written as a difference of kind of two terms which have the same structure. So in this way, if we define, this kind of average of JJ to be given by this form. Right? And of course, this has the meaning of current. At site J, between sites J and J plus 1. So this is the so-called continuity equation. So in this case, these particle numbers are conserved, right, of course. And related to this conservation law, there is a continuity equation. Right. Okay. So this is the kind of usual description of the time dynamics for ASEP in probability theory. And in this case, we usually describe the time dynamics using evolution for the function. But heuristically, maybe it is easier to think of time evolution of the probability in which a system has some configuration. A difficulty for the case of infinite space is that probability for having one specific configuration is usually 0 because there are infinite number of states. But in some cases, we can also consider finite dimensional state space. In this case, it is at least heuristically easier to consider time evolution of the probability in which the system has some specific, has a given configuration. And in this case, we also use a joint generator. A joint generator is, of course, described by, is denoted by L star. And for the at least finite dimensional case, this can be represented as simply some matrix. And the matrix is in this form. Of course, for ASEP on Z, this sum runs over Z, then this is kind of just a formal object. But if we consider periodic lattice, open boundary case, and so on, this is just another way of describing time evolution of ASEP. So this is a bit formal. Yeah. No, so, no. So this is okay. Okay, so that's a bit, yeah, you're not so used to it, right? So we suppose that at each lattice there are some two-dimensional space described by. So when there is a corresponds to 0. Suppose that at each site we have two-dimensional state, a space, linear space, which corresponds, in which each I equals 0, empty site corresponds to 1, 0, and occupied site corresponds to 0, 1, right? And we should think of the same two-dimensional space at all sites, and we are considering tensor products of this. And then corresponding to this tensor product, we can think of some large matrix which acts on this tensor space. And this J plus 1 means that this 4x4 matrix acts non-trivially only on the space related to sites J and J plus 1. And for all other sites, as just an identity matrix. So, well, yeah, so this can be 1, 1, 1, 1. And this big one matrix, J, and so on. Okay. Right. So right? So this is the kind of definition of the processes in a more formal way. Now we can ask about the stationary measure. For ASEP case. Yeah, so this was the problem I told you already. But in fact, at least for this ASEP case, the stationary measure is already classified, very, very well known. So basically, we only use the so-called Bernoulli measure. So in this case, the stationary measure is very, very simple. In fact, if we consider the so-called Bernoulli measure, in which all sites are independent, and each site is occupied by a given parameter, maybe rho, then this is the stationary measure. For the case of ASEP, there is another series of stationary measure, which is also a product, which shows kind of shock-like behavior. But in this lecture, we don't use this. So in this lecture, we just consider this Bernoulli measure as a stationary measure for ASEP. So at least if we put some extra condition that the measure should be translation invariant, this is the only stationary measure. So how can we check that this is the stationary measure? So I think it is a bit easier to use this description. So let me. So this describes time evolution of the probability at sites j and j plus 1. Now we are considering product measure, independent at all sites. So we can focus only on space related to sites j and j plus 1. And in this Bernoulli measure, sites j and j plus 1 are independent, and each site is occupied with a particle with a probability rho. So four-dimensional probability that they are in these states are simply given by 1 minus rho square, rho times 1 minus rho, rho times 1 minus rho, rho square. If you compute so if this is 0, that's easy, right? Because this means that this measure, this probability does not change after the application of the generator, adjoint generator. But in this case, there's something remaining. But this can be written as a particular in a particular form. So there is, we are considering tensor product, as I mentioned over there. And related to this tensor product structure, we can rewrite this in this particular form, in which we see the same vector appearing here and here with minus sign, and these are the same. And if you take a sum over J, this gives you some telescopic sum. So they just all cancel. So basically, this gives us 0. So in this way, we can check that this Bernoulli measure is the stationary measure for A set. And this fact that this is non-zero, even after acting generator, this is not 0, but this gives us some telescopic sum, is related to the existence of non-zero current for A set. For this measure, the current is not 0, and in this case, this becomes 0. But in this case, this is not 0, but because of this particular structure, the measure itself is 0, i.e. stationary. So what is the current for this state? So for the general case, the definition of the current is given here. But now we specify the measure. So we can just try to calculate this average current for this particular measure. Right? What is that? Easy, right? So eta j is simply replaced by rho. 1 minus eta j is replaced by 1 minus rho. So this is simply given by p minus q times rho minus 1 minus rho. So this is the current for this Bernoulli measure with parameter rho. Oh, yes. Yeah, yeah, because this is Bernoulli measure. Maybe we sometimes J of rho. And of course, in general, current can depend on the position J, but because of this stationary invariance of the Bernoulli measure, now this is simply a function of rho and P and Q. Okay. Once we have the average current, maybe we can try to write down hydrodynamic equations for ASIP. We have time evolution for the density, and we have continuity equation, and now we have explicit expression for the current. So but maybe it is easier to start from the SEP case. So now we are considering symmetric case. In this case, so maybe I come back to the definition of this current. In this case, when P is equal to Q, there is something spectacular happening. So of course, in this expression of the current, the non-trivial part is the kind of nonlinear term, which depends on eta j squared, right? But when P is equal to Q, they cancel. So this is simply given by a difference of j and eta j plus 1. So then the time evolution for the average density is given by this. So this is easy to solve, I think. This is just a discrete diffusion equation, which can be solved by Fourier analysis. But this is already a very, very non-trivial fact about the symmetric exclusion process. After all, we are considering infinite number of particle systems, right? But this equality says that if we focus on this particular so-called one-point function, density average, then this satisfies simple linear equation, closed equation for one particle system average. So this is the manifestation of the, this is the kind of simplest case of the self-duality of the exclusion process. In fact, there is a generalized notion of the self-duality for A set, which is also very, very useful. But this is a kind of simplest case for the set case. Anyway, so because if this is the equation for one-point function, then the hydrodynamic equation should be easily obtained, and this should be the diffusion equation. So if we suppose that now we have to do some scaling. J is taken to be x over epsilon, and the t to be t tilde over epsilon squared, so epsilon squared, and then we rename t tilde back to t, and then, of course, if we suppose that sorry, I have been omitting the t dependence, but of course we can introduce time dependence t here. Then, if we denote naively this expectation value for jt with this scaling, then this u should satisfy the diffusion equation. So this is the kind of hydrodynamic equation for the set case. Of course, this is not completely rigorous. Of course, but still, at least for this case, it's not so difficult to give a real proof. But anyway, this is the correct result. But the hydrodynamics equations for set is simply given by diffusion equation. Right. But this is maybe looks too simple. Sorry, UXT is it's like here. So this becomes basically U, yeah, and this becomes the second derivative with respect to x. What about the A set case? In this case, of course, there's no such a nice cancellation of the nonlinear term, so we have to deal with nonlinearity. But you know, for the Bernoulli measure case, in which all sides are independent, we simply replace the kind of two-point function by a product of one-point function, and we get this. But maybe in the hydrodynamic description, maybe we can just do the same. Then then even when there is a dependence on x and t in U, so of course, for the Bernoulli measure in which they are independent, we can really calculate them to be rho times 1 minus rho, which does not depend on t and x. But maybe we can also suppose that even when they are depending on x and t, in the hydrodynamic limit, maybe this can be replaced by u times 1 minus u. If we assume this, then now with a different scaling, from the continuity equation over there, we get this equation. Sorry. Of course, this is just a parameter, so this is not very important. Du dt plus, dx of u times 1 minus u is equal to 0. So this is the well-known Borgo's equation without viscosity. And even though this is too heuristic, it is known that this is the correct hydrodynamic description of the ASEP when P and Q are not equal. So ASEP is really microscopic model with the stochastic dynamics. But when we are only interested in hydrodynamic description, so kind of average behavior of the system, we can simply use this equation. And if we can solve this equation, then basically yes? So the scaling is different. Yeah. So this is now epsilon. Yeah. But if you recall the Navier-Stokes equation, this is a little bit similar to the Navier-Stokes equation. In the Navier-Stokes equation, that was the equation for velocity and not for density. But if we just identify them, then there's a time derivative, and there's a nonlinear term, quadratic nonlinearity. And then on the right-hand side, we have also nu times Laplacian of v. So there's no Laplacian term here. But this kind of term can also appear in the description of hydrodynamic description of ASEP, which is the so-called WASEP. W means weakly. Weakly means that when we consider some scaling, we also take smaller and smaller asymmetry, right? By doing this, maybe some extra term remains in the hydrodynamic equation, and this is really the case. Okay. To see that, maybe we can try to rewrite this average current in a slightly different way as a kind of combination of SEP case and ASEP case. So when P is equal to Q, this is 0. So this gives you SEP case. When P is equal to 1 and the Q, yeah. And then so there's this nonlinearity. And maybe now we can consider the scaling. This is, in a sense, closer to the diffusion limit in the sense that we scale time like this with epsilon squared. But now we also scale P minus Q epsilon. Yeah, in this limit, what do we get? So in this limit, we now get the again the Borger's equation, but with the viscosity here. And even for this particular limiting case of ASAP, the hydrodynamic description can be simply given by solving this equation. So we don't really have to solve the microscopic model completely, so we can just rely on this hydrodynamic description. So when we want to study maybe this Borger's equation without viscosity, there's some difficulty to solve this equation because it is known that for this equation itself, there's no uniqueness for the solution. But there's a notion of entropic solution, which is related to some entropy condition. Then we can specify some unique solution. But there's another way of considering this, taking up physical solution for the implicit Borger's equation is that maybe first we introduce this viscosity with a small parameter epsilon, and first we solve this. And then after solving this, maybe we can take epsilon goes to 0. Then this gives you the solution to this Borger's equation without viscosity, and this agrees with the entropic solution. But anyway, there's a way to select physical solutions to these hydrodynamic equations. Right. Okay. So what about the case? So these are the hydrodynamic descriptions, but we are also interested in fluctuations. How can we do that? So this is, of course, the main topics of this lecture, but yeah, this is the kind of basics before going to the fluctuations. For the case of TASEP, P is equal to 1, Q is equal to 0. So hydrodynamic is just a Borger's equation without viscosity, and the constant is just 1 now. Now maybe let's suppose that we consider the so-called step initial condition. As time t equals 0, all left sides are occupied and all right sides are empty. And we start from this particular initial condition. And we are interested in the current at the origin. And for the hydrodynamic description, it should correspond to the solution of the Borger's equation without viscosity for the initial condition given in this way. So you have to solve this equation, but here I just give you the solution. And it is known that the solution to this particular case, this entropic solution, or the solution which appears as a limit of epsilon here going to 0. So this is just given by a linear slope. And this position is t. So this can be expected from microscopic model because the first particle in TASEP just hops as independently, just like a random walk only in one direction. And one can simply calculate it to be, the average is like t, and this is reflected here. And this is symmetric. So at the origin, we have density 1/2. So the density 1/2 corresponds to the current 1/4 in this particular case, right? So from this hydrodynamic description, so we are now interested in the current at the origin, which is denoted by n of t. So n of t is a random variable. Depends on what kind of configuration is realized for each sample. But from this hydrodynamics, we expect that when t is large, this should be always close to t quarter. Of course, we should think that n of t divided by t goes to 1/4 in a certain sense. But what I want to say here is that now we are interested in the fluctuations around this hydrodynamic behavior. And if we naively think that there could be, maybe there's something like a central limit theorem for our system, maybe you'd expect that the fluctuation scales like t to the 1/2, and here comes Gaussian random variable. But this is not the case for the case of Qtative. And in fact, it is known that this scales like t to the one third. And here comes some non-trivial random variable which we are interested in. So this is related to trace rhythm distribution. Okay. Yeah, in fact. So, I will finish in a few minutes today. Okay. So it's already almost 20 years ago, but for the fluctuation of this current, so this was the kind of the beginning of this whole integrable probability almost. And 20 years ago, he proved that so this is the quantity we are interested in, current for integrated current at the origin for Qtative with the step initial condition. This is random variable. From hydrodynamic description, we expect that the average behavior is like t quarter, so we subtract it. And we kind of know that this scales like t to the 1/3, so we divide by this 1/3. And then we should put some coefficient here, which turns out to be given by this value. Then so this is a random variable, scaled version of the current. And then we are expecting that this, as t goes to infinity, this goes to some non-trivial random variable. And we are considering distribution, cumulative distribution function of this random variable. And in the t goes to infinity limit, this goes to some distribution function denoted by f2 of s. So this is the GUE trace rhythm distribution. Okay. So today I wanted to explain how this appears, but maybe this is for tomorrow. And yeah. So here, so this distribution appears as the limit of distribution function for some current in non-equilibrium problem, right? But originally, this appeared in the context of GUE, so random matrix theory. And how to see this trace rhythm distribution in the context of GUE is now very, very standard. So I already prepared some notes, which was already posted on the web page of this summer school, so you can take a look. And I wanted to explain a little bit about it in this lecture, but maybe I want to do it in the exercise session, and exercises are also taken from there too. Okay. Okay. Thank you for your attention. Yeah.
Any questions? Yeah, okay, let's continue with the exercise section, half an hour. Oh, question?
Oh, question? Yeah. So which case? Viscous, Wasep case or W, Wasep case. I don't know why. From here, so this is a kind of combination of SEP case and general ASEP case. From here, so the current is now separated into two pieces. So this corresponds to basically SEP case. From here, you get diffusion equation. And this corresponds to general ASEP case, which gave us the nonlinear term in the Borges equation. And the P minus Q becomes 0 in this diffusion limit in the if P and Q are fixed. But by taking P minus Q to be small, which is compatible with this diffusion scaling, then this part remains, and then this gives us sorry, maybe this should be sorry, so P minus Q should not appear here, sorry. Thank you.